Hi grade 12s and welcome to this video. In this video, we are going to be working on the Euclidean geometry section of the November 2024 paper 2 exam. Okay, so this is what we have in question 9. Remember that they tell us to provide reasons for statements in questions 9, 10, and 11. So question 9 says, in the diagram, ABCD is a cyclic quadrilateral. So this is a cyclic quad, and we can use all cyclic quad properties on it. And then they tell us that BC is produced to E, and we have AC is drawn, and then they give us some dimensions that we need to put down. So angle A1 is half the size of angle B. That's the first thing they tell us. Angle A1, this angle is half the size of angle B, this entire angle. Let's just keep a mental note of that. Okay, so we might actually as well write it down. So we might as well just put that down so we don't forget. This is a half of angle B. Keep that in mind. And then they tell us that angle A is 46 degrees, as we can see, and angle C1 is 86 degrees. Okay, so the first question is, calculate with reasons the value of angle A1. Okay, angle A1 is this. And as you can see, it relates to angle B. Instead of thinking in that direction, let's just think about, because the thing is, if you're trying to relate it to angle B, we don't know what angle B is. So it's not very helpful to look at it like that. Let's look at the fact that we have a cyclic quad here, right? If this is a cyclic quad, what do you know about the exterior angle of a cyclic quad? The exterior angle of a cyclic quad is always going to be equal to the opposite interior angle. So that angle, that's what it's going to be equal to. Okay, so we can work with that. So this is what this means. We're going to say the exterior angle is angle C1, right? So angle C1 is going to be equal to, and is equal to the opposite interior angle. So this entire thing. Okay, so that's angle A1 plus the 46 degrees that we have there. Okay, so angle A1 plus 46 degrees. Might as well just put the numbers. So angle C1 is 86 degrees and A1 plus 46 degrees. And then we just have to solve for angle A1. So if you left angle A1 alone on this side, right, you still have 86 degrees and you'll take 46 degrees over. And so do you see that angle A1 is going to be equal to 40 degrees? So we can actually just conclude like that. Angle A1 is equal to 40 degrees. And then the reason was because of the exterior angle of a cyclic quad. And that is our answer. So that is for 2 marks. Moving on to the next question. The next question, 9.2, says, hence prove that AD is equal to DC. Okay, let's see what they're speaking about. They want us to prove that AD is equal to DC. Okay, that doesn't seem like a bad thing to work with, because here's the thing about proving these two sides are equal. Do you see that these two sides are included in a triangle? This triangle, ADC or ACD. Because of that, that is very helpful. So because they're included in this triangle, what we can focus on in this triangle is if these two sides must be equal, then we can actually focus on the two angles that should be equal to make these sides equal. Okay, so do you remember that rule that says if you have a triangle and you have two sides being equal in the triangle, then it means that their opposite angles, right, would also be equal. Angles opposite equal sides are equal, okay? So the way this is working is the other way around. They want us to prove that the sides are equal, but we clearly have to show them that there are two angles that are equal here. And if those two angles, if we actually do find them to be equal, it would mean automatically their opposite sides would be equal. Okay, so that's really what we're working with here. Okay, so what are the two angles that we're supposed to show them are probably equal to each other? It would be this angle over here, angle A1, and angle C2. Now, we already know what angle A1 is. It is 40 degrees. So all we need to find is angle C2. And we're going to find out that angle C2 really is equal to 40 degrees as well. Okay, so we already know that angle A1 is also equal to a half of angle B, right? So this can actually help us find angle B. So let's just think about this. How will angle B help us to find angle C2? Because that's what we really need to focus on. How is finding angle B going to help us with angle C2? Okay, so if you look at this shape, let me actually just remove what we have here. Just look at this. This is a triangle. And then this is the exterior angle of the triangle. The exterior angle of a triangle is equal to the sum of the two opposite interior angles. So angle A2 plus angle B would give you this entire angle C1 and angle C2 joined together. Okay, so that's how it's going to make sense. So we are still focusing on finding angle C2, and how we're going to find it is by using what we know here. We know now that angle A1 is equal to 40 degrees. Okay, so we know that. We just tell them this is 40 degrees. We know that. But we also know that angle A1 is equal to a half of angle B. So this can help us to find the size of angle B. So angle A1 is equal to a half of angle B. You don't even need an equation to find this. You need to think about it without an equation. If A1 is 40 degrees and it's equal to half of angle B, then it means that angle B is 80 degrees. Okay, so this is 40 degrees and we know that it's half of angle B. You could decide to divide both sides by half or multiply both sides by 2 and you would find angle B. Okay, so if you divided both sides by a half, angle B would be equal to 80 degrees. Okay, so that's what we have there. Since A1 is half of angle B, since it represents half of it and it's 40 degrees, then that one is 80 degrees and still represents half. Okay, so this is what we have. Angle B is equal to 80 degrees. And how can we use that now? So now that we know this is 80 degrees, remember, exterior angle of a triangle. So we're going to use this is the exterior angle because it goes from the extended side of the triangle all the way to the triangle. So this is going to be our equation now. We know that the exterior angle of a triangle is equal to the sum of the two opposite interior angles. So that means that angle C1, which is 86 degrees, plus angle C2, that's the exterior angle. So angle C1 plus angle C2, let's just put the actual numbers. 86 degrees plus angle C2 is equal to, that's the exterior, is equal to the sum of the two opposite interior angles. 46 degrees plus 80 degrees. So 46 degrees plus 80 degrees. And then we can tell them that's because of the exterior angle of a triangle. Okay, it's very important to say the shape because you see this is the exterior angle of a cyclic quad. This is the exterior angle of a triangle. Two different things. Okay, so let's just go ahead and add and simplify. So here we have angle C2 is equal to, when you add these together, 40 plus 80 is 120. So this is 126 minus 86 degrees. Okay, 6 and 6 is gone. 120 minus 80 gives you 40. So angle C2 is therefore equal to 40 degrees, just like we knew it was going to be. Okay, and now that we know that this is 40 degrees, this helps us a lot because this is also 40 degrees. So you have a triangle that has two angles equal. Okay, because those two angles are equal, automatically it means that the opposite sides of these angles, the sides opposite these angles would also be equal. So therefore it means that AD is equal to DC. Okay, so we can finally conclude that and give them a reason. So our reason will go like this. If the first theorem of this triangle that we know with equal sides, right, is where you have two sides that are equal, and then the reason is angles opposite equal sides are equal, then you can just say this one is sides opposite equal angles are equal. It's just the other way around. Okay, so it's really just the converse theorem of that. And that is it for question 9. And we move on to question 10. Okay, so we have proven that. Moving on to question 10, we have a proof. Okay, so 10.1 says, in the diagram triangle RST is drawn and we have line AB intersects RS, okay, and RT at A and B respectively, as we can see that happening over there. And then they tell us such that AB is parallel to ST, as we can see. Here's the theorem they want us to prove. Prove the theorem which states that the line drawn parallel to one side of a triangle divides the other two sides proportionally. That is, RA over AS is equal to RB over BT. Okay, this is a proof I have on my channel. It's actually one of the longest proofs. The only reason it's long on my channel is because I explain some background knowledge that you should know about the heights and bases of triangles before you can understand that. So I'm going to link that video here in the description. I want you guys to actually take a look at it because I'm not going to explain the background knowledge. I'm just going to say it as it is. So if you want to find out why certain things work the way they do, you can actually check that video out. Okay, so let's start with this proof. Now, how we work through this is like this. We're trying to prove the proportionality theorem, but focus on the sides that you have stated here. They say RA, okay? RA is this over AS, and then RB over BT. Those are going to be very important sides that we're going to look at. So in order to prove this theorem, because you need them to be over each other, we're going to work with the areas of the triangles. But the thing about the areas of these triangles is they have bases. And these lines that we see here, RA, AS, RB, BT, those are going to be the bases of the triangles. So with the top triangle, it's pretty simple to see that RA can be the base of that triangle. This can actually be the base of the triangle. But then for you to be able to find the area of this triangle, you need a height. Okay, we're not really using trig here. We're not using the area rule to find this. So we need a height. So what we're going to do is construct the height. If we can use this as a base of this top triangle, let's construct the height. The height is always going to go from the base to the highest point of the triangle, and it must be perpendicular to that base. So how we're going to draw it is from B, and we draw down to RA, and it is perpendicular to RA. And we can go ahead and call that H, so height, that height there. And then do you see that RB is also being mentioned here? So we're also going to take it as a base of this same triangle, but we're just going to look at this like a different triangle. But it's still the exact same thing with the same area value. Okay, so we also need a height for that since this is the base. So the height is going to go from the highest point of this triangle. You would have to tilt your head this way to see. The highest point will be at A, and then we go down, and it needs to be perpendicular to that base. And we can call that height K. Okay, so that's what it looks like, and we're going to tell them everything that we have constructed. So we're going to tell them about that perpendicular heights that we constructed and from which places really they were constructed. So you can just say construct the perpendicular height from B to line RA. Okay, I'll call it AR. And then the second one, that height K, we're going to say construct the perpendicular height K from A to line RB or BR. Okay, so now that we have all that constructed, we still need to focus on the fact that these are also going to be bases of triangles. All of these are really just bases. And the idea behind that is, you know how the area of a triangle is a half times the base times the height. Okay, if the heights are the same, they're really just going to cancel. And if the halves are the same, they're going to cancel. So that leaves us with the base, these values. And that's what we're really just trying to do. Keep those values there. Okay, so the next base that we have is AS. And if you look at AS, it doesn't look like the base of a triangle right now. Okay, and that's because right now we don't have that triangle that has the base of AS. We have to construct it. So how can we construct a triangle that is going to have a base of AS? Well, if you construct a line from S to B, look at what happens. You now have a triangle there. You now have a triangle ASB or ABS. There, you have a triangle now and it has a base AS. Okay, so that's the first triangle we construct. Then we also need a triangle with a base BT. So how we can do that is by constructing a line from A to T. So line from A to T, and there we go. Now we have a triangle over there that's ABT with a base of BT. Okay, so we're also going to have to tell them about those constructions. Just construct line, BS, and AT. That's all. Okay, so we are done with constructing, and now let's get to the proof. Okay, so we have our triangles down. We have everything that we need. Now, remember how we have RA first over AS. We're going to use these areas like that as well. So to make sure that RA is on top, we're going to focus on the triangle with the base RA. And that is this triangle ABR. You can call it any way you want. BRA is still fine. Okay, but I'll just put it in alphabetical order. So ABR. So we're going to focus on the area of this triangle. Remember, we're focusing on area because of that half base times height. So we're going to say area of triangle ABR. And we're going to put this over the area of the triangle with a base AS so that we can form this over here. Okay, so which triangle has the base AS? It would be this triangle, remember? ABS, that triangle. So over the area of triangle ABS. So say that their area of triangle ABS is equal to, and now we're just going to expand this. How do we find the area of triangle ABR? By saying a half multiplied by the base. So what is the base of ABR, that top triangle? We're using this as the base, right? RA. So a half times RA multiplied by the height, the perpendicular height. What is the perpendicular height of that triangle on top? The perpendicular height of this triangle, okay, with this base is this line. That's H. Okay, so that's what we have there. So we're going to tell them this is multiplied by H. And then this goes all over a half here times, again, the base of this triangle ABS. So the base of the triangle ABS, this triangle, right, is AS. So when you look at that triangle ABS, what is the height? If this is the base, what exactly is your height? Your height, looking at it like this, it's not AB. I know it looks like it's AB, but it's actually not AB. The height always goes from the highest point of the triangle down, and it needs to be perpendicular to the base, or at least the extension of the base. If you take AS and you extend it, right, it extends to this point. And if you go from the highest point of this triangle down to this line, which is an extension of the base, you see that it is perpendicular. So what that means is that H is also going to be your height. And you can check that video out for a deeper explanation on this. Okay, so that is the height that we have. The perpendicular height of this triangle is H, okay, by construction. So this is a half times our base, which I didn't even write, it's AS, and then multiply by the height, which is H as well. Okay, so you see how this is going to work out here. The half and half would cancel, the H and H would cancel, and all you'll be left with is RA over AS. Okay, that is great. We have RA over AS, and now we just have to focus on RB over BT. So we're going to do the same thing. Focus on the areas that have these bases. So RB, which area has the base RB? Which triangle's area? Okay, it will be this triangle again, but this time we focus on this as the base. If that's the base, then where's your height? The height of the triangle with this base is K, from the highest point down to the perpendicular base. Okay, so we're going to go and say this is, again, the area of that top triangle, which is the same thing as that other one. So you can call it the same thing. So triangle ABR, but this time we're using a different base, over the area of the triangle with a base BT. So the triangle with the base BT, as we already saw, is this triangle ABT. So that's the base. And so what is the perpendicular height? If this is the base of this triangle, right? This is the base. What's your perpendicular height? It's going to be from the highest point to an extension of that base. As long as it's perpendicular, that makes that the height. So K is your height. Okay, so we're going to say it is the area of triangle, and we're focusing on that triangle ABT, and we have triangle ABT is equal to, okay, and now we can just write everything down. So a half multiplied by the base of that top triangle is BR, okay, BR, and then is that really what they call it? RB. Okay, I'll focus on what they call it, RB. And then times the height. We saw how the height of that one with that base is K. Okay, so that's K. And then over this one is a half times your base, which is BT, as we saw, this triangle, BT, and then the height is also K. So K. Same thing happens here. Half and half cancels, K and K cancels, and all you're left with is RB over BT. Okay, so we are almost there. We got RB over BT. Great. The only thing now is, you see that these proportions are equal. So how do we show them that they will be equal to each other? Well, with the first triangle, it's very simple, because as you can see, the first triangles that we used was triangle ABR and triangle ABR. They're obviously the same triangle. They have the exact same area. So that is a given. You can tell them that. You can tell them, but we know that triangle, or the area of triangle ABR, is equal to the area of triangle ABR, which is something you really do not have to mention. I'm just putting it in. But now that those two are equal, it doesn't really tell us that these two are equal. Let's look at those two triangles, ABS and ABT. Okay, so when you look at ABS, and I can remove these now, we don't really need that anymore. Look at ABS, right? And look at ABT. What do you notice about these two triangles? Do you see that, first of all, depending on how you look at them, they actually have the same base. So if you look at them as if they have this common base, AB, okay, so that is now your base, then you see that these triangles, right, are sharing the exact same base, first of all. So AB is their common base. But there's another thing that we also see here. Do you see that these two lines are parallel? Okay, so because these two triangles lie between parallel lines, their height is exactly the same. Okay, it's not like this one is going anything higher, nothing like that. They have the exact same height. Okay, so that would actually mean that this triangle, right, and this triangle, they have the exact same area. You could even flip this one around and place it on that one. So because they have the exact same area, they are also equal. So let's conclude by telling them those areas are exactly the same. So we also figured out now that the area of triangle ABS and ABT are equal. So area of triangle ABS is equal to the area of triangle ABT as well. Okay, and we can of course tell them the reason, because they have the same base AB and they're between parallel lines, so they have the same height. Okay, because they have the same base and equal height, since the triangles lie between parallel lines. So all you need for the two areas to be exactly the same is their base needs to be the same and their height needs to be the same, because the area of a triangle is found by saying a half times the base times the height. So if the base and the height are exactly the same, it makes the areas of those two triangles exactly the same. Okay, so now that we have shown them that, that would mean that the area of triangle ABR over ABS, right, those over each other, is or are indeed equal to the area of triangle ABR over ABT. Okay, since we are able to show them that each of those individual areas of those triangles are actually equal, that these two areas are equal and those two areas are equal. Okay, so that means that they would be equal to each other like that as well. And you know how when we found the areas of those triangles over each other, they got simplified to this, RA over AS. So that concludes that RA over AS is equal to, and those ones, they simplified to RB over BT. So equal to RB over BT. And there we go. We have proven exactly what they asked us to prove. Okay, so that is it for that proof. It is 6 marks. And we move on to the next question. Okay, so we are now on 10.2, and 10.2 says, in the diagram, O is the center of the circle, and then we have triangle PWS. So triangle PWS, okay, is drawn with P, W, and S on the circle. Okay, OR is perpendicular to PS. You can already see they're trying to use the proportionality theorem over there. Okay, and we have PRS is produced to T. So this line just gets produced to T. SW and OT intersect at V, so these two lines intersect at V. And lastly, yeah, that's something we need to take down. So OV is to OT is 1:4. Okay, so OV is to OT, that is 1:4. Okay, so we can put these ratios down as variables. So remember how ratios work. They're not the actual lengths of the line. They're just, if you had put these lengths, the actual lengths over each other, they would have simplified and be shared in a ratio of 1:4. Okay, meaning OV gets one part of it and OT gets 4 parts of it. So how we can express this is OV can be expressed as, for example, A. And if OV is A, that makes OT 4A, since it's 4 parts of whatever A is. Okay, it's very important to put those kind of things down so you don't forget that you actually did have ratios before. Okay, the first question is, prove with reasons that OR is to WS is equal to 1:2. Okay, OR is to WS. Prove with reasons that OR is to WS. Okay, yeah, as you can see, they're using properties or lines that come from this triangle. Okay, is 1:2. That is a very important ratio to think about. So OR takes 1 part and WS takes 2 parts. Where have you seen that before? Where you have a triangle like this and you have this side being half the size of this side. That is in the midpoint theorem. Okay, so clearly they're using midpoint theorem here. Now that we can see that they're using the midpoint theorem from that ratio, let's actually just prove to them that yes, OR is to WS is equal to 1:2. So what are the things that we need to focus on to be able to prove that? So with the midpoint theorem, you just remember what it looks like. Let me just give a backstory on it. So with the midpoint theorem, you have a triangle. It doesn't have to look like that triangle. And then you have a line drawn parallel to one side of the triangle. But here's the thing that you need to notice that you will be given in the midpoint theorem. Say this is ABC and this is DE. The thing that you will be given in the midpoint theorem is that AD is equal to DB. Okay, you're first told that. So AD equals DB. And then you're also told that DE is parallel to BC. So, and DE is parallel to BC. And then since you're given that, the conclusion would be this. If you are ever given this scenario, what we would conclude from this is, therefore, this means that AE is going to be equal to EC, first of all, right? And the second thing that we can conclude is that, you see BC, right? It's going to be double the size of DE. Or we can even see it as, this means that DE is half the size of BC. So if this was 20 centimeters, then that makes that 10 centimeters. Okay, so that is half of that. And as you can see with that, that's really what they're saying here with this ratio of 1:2. The only way that that can be shared in a ratio of 1:2 is if you have this midpoint theorem situation over here. So this gets 1 part and that gets 2 parts. Okay, so let's focus on what we need to have. We know that that is the conclusion, but for this to be like the midpoint theorem, we're going to have to clearly have what is in red here, okay? One side should be equal to another side, and then the two lines should also be parallel. Okay, so that's what we're focusing on. In this, okay, we can already see it clearly here. So in this big triangle, what are the two sides that are clearly equal? Look at OP and OW. Those are radii. So you have two radiuses. They're obviously equal. So we already have two sides that are equal. And now all we have to show them is that OR is somehow parallel to WS. Okay, so how does that work? Okay, with this one, they're actually making it really, it's not too bad. Do you see that because this is a radius, this is also a radius, so this is a diameter. The angle in a circle supported by a diameter is 90 degrees. You see how those are both 90 degrees? If that's 90 degrees and this is 90 degrees, you have corresponding angles. Corresponding angles can only be on parallel lines. So if you have two equal angles in the form of corresponding angles, it makes those two lines parallel. Okay, so there. So that's how you can think about it and unpack it. Okay, so let's go ahead and just show them what we need to show them for us to conclude that this really is shared in a ratio of 1:2. So it was first the radiuses, radii being equal. So tell them that OP is equal to OW first of all. OP equals OW, and that's because of radii equal radii. And then the second thing is about that being 90 degrees. Okay, so let's just show them that this is really 90 degrees. We have a diameter and it's supporting an angle, which is 90 degrees. So angle, I can't really call it angle S because it also has this side. So let's call it angle PSW. So angle PSW is equal to 90 degrees. And the reason why is because it's the angle in a semicircle. Okay, and since that is 90 degrees, that means we have corresponding angles. So we are concluding that these two lines are therefore parallel. So OR is parallel to WS. Okay, so therefore OR is parallel to WS. And our reason for that is going to be because we have corresponding angles. And then you can also just emphasize the angles that are equal, okay, that you can see there. Or what we could have just done is actually just show them that they are equal. So tell them that angle PRO is equal to that angle PSW. So PRO equals angle PSW. And they will be able to see that already. Okay. And then finally tell them that these two lines are parallel. So OR is indeed parallel to WS. And that is because of corresponding angles. And now with that being said, because we have these two lines being parallel and these two lines being equal, do you see that this is actually the midpoint theorem? Okay, because we are given that this side is equal to this side and these two lines are parallel, we can conclude that this line OR is half the size of this line WS or SW. Okay, so that's what we can tell them. So therefore, this means, and then our reason will back us up. So tell them that this means that OR really is equal to half the size of WS. And our reason would be the midpoint theorem. Okay, this is because of the midpoint theorem. So since we have that now, you can actually still make it look like that. Look at what we can just do here. We can divide both sides by WS. And then so WS and WS. Or you could really just say it with logic because it's really the same thing. So OR over WS is therefore equal to, you see that those cancel there, it's equal to a half. So that proves that OR is to WS is equal to 1:2. Like that. Okay, so that's another way that we can just write it down. Okay, but this whole arithmetic doesn't really matter that much. It's the logic about it, because these are just two different ways of representing a ratio. Okay, so this ratio ultimately works because of the midpoint theorem. So that is for 5 marks. And moving on to the next question. Next question is 10.2.2. Okay, so question 10.2.2 says, calculate the length of PT if ST is 15 units. Okay, let's put those down. PT. Find PT, that whole thing, if ST is 15 units. Okay, so if this equals 15 units, what exactly is this entire length? Okay, how can we find that? There's some ratios that we know now. We know these two. I don't know how helpful they would be right now, but we'll just keep that in mind. Okay, so now another thing that I just remembered is with the midpoint theorem, right? Once you've proven a theorem, it means that all the properties of that theorem, you can use it in that shape. See how we've proven that we use the midpoint theorem in this triangle, right? In this triangle, PWS, right? And you know that the full midpoint theorem says these two are equal, these two are parallel. Therefore, these two must be equal. Okay, and then this is half the size of that. So I'm already going to put those down. I don't really need any other theorem to tell me that because the midpoint theorem has already proven that. Okay, so we know now that PR really is equal to RS. Let's keep that in mind, and that will probably be very helpful in what we're going to work with now. Okay, so already looking at this, with what we're working with now, it seems like you're going to have to use this triangle, this bigger triangle over here. Okay, but you see with this bigger triangle, the two lines that are parallel in it are RO and SV. Okay, so the triangle we're really going to focus on is this triangle. And there's no problem with focusing on that. Even if PT also includes this, it's not a problem because do you see that PR and RS are the exact same size? Okay, so if you know what RS is, you know what PR is. So we can focus on this triangle. And we already have two sides being parallel. Okay, okay, so with this one, we can focus on that triangle. Yes, definitely. And we can use the proportionality theorem. You know, in order to be able to successfully use that theorem to actually find a missing side, you must have a situation where you have at least the ratios of one hand side, which we do. Okay, we have 4a, okay, being OT, the ratio of OT is to OV, or OV is OT, right? We have ratios for that. And then on this side, what it would be paired with, right, would be RS over RT. And like that, it may not be useful. And the reason why is because we don't know what RT is, neither do we know what RS is. So we can actually just change the way we use this. Because we already know these ratios, how about you use it in a way that will actually be helpful to find one of the sides in this triangle so that you can, at the end of the day, find PT. So here's how we can actually use this. Why don't we use it like this? Say RS, right, over ST. And then the way we would use it on this side, because we know this is OV is to OT, right, as A and 4A, we can actually just use this like this instead. Instead of saying it like that, we can say OV is to VT. Okay, but you would know that we already knew OV was A, and so this makes VT 3A since OT is 4A. So this plus this must give you 4A, right? So that means that this is 3A. Okay, so you see how that helps us with this. So yeah, that's how we can actually use this. So we can use this right now to find the length of RS. And then once we find the length of RS, we will know exactly what PR is since they are equal. And once we know what that is, we would be able to see the full length of PT. It would be this PS, right, added with ST, which is already 15 units. Okay, let's go. So I'm going to say RS over ST in that order. So RS over ST, that should be equal to, that ratio should be equal to OV over VT. OV over VT, and then just give the reason. OV over VT. And the reason is because we have a line drawn parallel to one side of the triangle. The proportionality theorem, really. Okay, so the only one we actually don't know right now is RS. And we're going to find it because it helps us to find PT. So RS over and then ST. ST we actually know. We know it's 15 units. So we'll take it as over 15 is equal to OV. OV just takes A, or you could say 1. It's the ratio 1. And over VT, which is 3A. And that's the ratio 3. Okay, this is why it doesn't matter to write it like this, because you see that the A's would still cancel and then you still have your ratio. Okay, so therefore this means we have RS over 15 is equal to 1 over 3. And we can solve for RS. So just get rid of the 15. Multiply both hand sides by 15. Therefore, RS is equal to 15 times 1 over 3 is really 15 over 3. 15 divided by 3 is 5. So 5 units. That's what RS is. Now that we know what RS is, since that is 5 units, 5, then that makes PR also 5, since they're equal because of the midpoint theorem. So PR is equal to 5 units as well. You can also just remind them midpoint theorem. Okay, and therefore we can now find the full length of PT, which they asked for. So if these are both 5, 5 and 5 and 15, the full length of PT is 25, okay? 10 plus 15. So therefore, PT is equal to 25 units. And that is our answer. Okay, so that is it for question 10, and then we move on to question 11. We are now on question 11, and question 11 says, in the diagram we have A, B, G, F, and they lie on the largest circle, okay, on a larger circle. And then we have a smaller circle is drawn to touch the larger circle internally at A. So this smaller circle is drawn and it touches that larger circle as at A, as we can see. And then they tell us that EA is a common tangent. Okay, tangents are very important, so let's keep that in mind. EA is a tangent in the small circle, okay, and the big circle as well. And EBCF is another tangent to the smaller circle at C. So as you can see. So just remember, for the smaller circle, it has two tangents. For the bigger circle, it has one tangent. Okay, and then AC is produced to G. Okay, those are just lines that it's speaking about. AF cuts the smaller circle at D, and AB, CD, and GF are drawn. Okay, other lines that they mention as well. So the first question is, if EAG, that angle, is equal to X, you need to determine with reasons 4 other angles equal to X. Okay, so EAG is equal to, yeah, okay, that's not a bad start. If this is equal to X, EAG, right? Find 4 other angles that will also be equal to X. So a good thing is this is being drawn where we have a tangent. And this tangent, remember, this specific tangent AE is a tangent to the smaller circle and the bigger circle. So we can use a tan chord theorem in 2 places here. So we probably already have 2 answers for X here. So focus on the fact that this is a tangent, and let's look at the smaller circle first. If this is your smaller circle and that is a tangent, remember that the angle between the tangent and a chord, in this case the chord would be AC, would be equal to the angle opposite that chord, or the angle supported by that chord, which is angle D1. So it means that angle D1 is also equal to X, okay, because of the tan chord theorem. We also have another situation with the tan chord theorem if we look at the bigger circle. So look at the bigger circle. If A is a tangent to the bigger circle, then the angle between the tangent and the chord, since the angle ends here, this is the chord AG, would be equal to the angle supported by that chord. Okay, so it's this entire angle that is equal to X as well. Okay, so let's just put that down. So we have 2 already, 2 more to go. Let's go. That first one is this angle D1. So angle D1 is equal to X, and you can tell them is because of the tan chord theorem. Okay, and the second one is that angle. Let's just call it AFG, since it has 2 angles in it. AFG is equal to X as well, also because of the tan chord theorem. Okay, we've got 2 angles equal to X. That's great. Let us see any other angles that would be equal to X. Okay, so looking at this, in the topic of tangents, looking at the smaller circle, the smaller circle has 2 tangents. We already saw that in the beginning, right? So since the smaller circle has 2 tangents, look at that. Okay, that's a tangent, that's a tangent. What do you know about tangents drawn from the same point? They are equal. So you have an isosceles triangle here. Since you have an isosceles triangle, that makes angle C1 also equal to X. Okay, so we can actually tell them that. So we'll first tell them about AE and CE being exactly the same. So AE is equal to CE because of tangents drawn from the same point are equal. Okay, this is specifically tangents drawn from the same point to a circle are equal. Okay, so since those are equal, that makes that an isosceles triangle. And so that means that angle C1 is also equal to X. So we can tell them that these 2 angles are equal. Angle C1 is therefore equal to that angle that we started off with, EAG. Okay, so which is equal to X, of course. So those 2 are equal. Okay, so we've got 3. 1 more to go. Okay, let's just see in our diagram what else we can find. I'm going to keep that those 2 lines are equal now, since we found out that. So this is also X, but these 2 lines are now equal. What else would be equal to X? Okay, this one is quite clear. You see, the minute C1 is equal to X, these two are two lines intersecting, so we have vertically opposite angles. So that's also equal to x. Okay, so that's the last one. Angle C4 is equal to angle C1, which is equal to x. And that's because of vertically opposite angles being equal. Okay, vertically opposite angles. Done. And we have 4 angles equal to x. Moving on to the next question. Okay, 11.2. So 11.2 says prove that AG multiplied by AD is equal to AC times AF. Okay, the minute they start mentioning lines, you just need to draw them down so that you can see where these lines are and then relate it probably to some sort of triangle or something. Okay, so AD and AG, where are those? We have AD over here, and then AG is that. Okay, and then AC and AF. AC is this one, and AF is on the other side. Okay, I think we can already see what's going on here. It kind of looks like it looks like a proportionality theorem kind of thing. Yeah, and it's definitely that case because yes, I know that they didn't tell us that these two lines are parallel. But do you see that we also have corresponding angles here as well? See, angle D1 is equal to angle AFG, right? So that would make these two lines parallel. So that's probably where they're getting that from. So we're going to use that. We're going to use this triangle and really the proportionality theorem on that, using those lines they mentioned, and then we'll just divide and it will get to that point. Okay, so we can't just start using it. We have to show them that these two lines are parallel. So as you can see, because these two are equal, it makes that parallel. So we can conclude, first of all, these two angles are equal, therefore those two lines are parallel. So angle D1 is equal to angle AFG. Let's tell them that first. Angle D1 is equal to angle AFG, and we can see that because they're both equal to x. So that concludes that CD is parallel to GF. So line CD is therefore parallel to GF, and this is because of the corresponding angles that we saw that were equal. Okay, so now that they are parallel, you can actually just write that down. These two are parallel. And now we can use the proportionality theorem on these. Okay, so we can see the lines that they used. So we're going to take it as AC over AG because those are the lines that were mentioned. So AC over AG is equal to, okay, it's in proportion, so is equal to AD over AF. Okay, so AD over AF, and then tell them the reason because we have a line parallel to one side of the triangle. Okay, so now that we have that, we just have to get it to look like this. So you see in this, we have AG and AD. So it just means they cross multiplied. So if you say AD, if you say AD times AG, okay, we get AG times AD is equal to, and then cross multiply again. So AC times AF. That's all they did. Okay, so there we go. And we have proven that. So done. That is for 4 marks. And then we move on to the next question. Okay, so next question, 11.3. Yeah, says proof that we have this triangle similar to that triangle. So let's again just highlight these triangles and then we'll look at it and think about how they can be actually similar. Okay, in all of these, they didn't give us any dimensions. They didn't give us sides, right? Telling us that anything is 10 units or anything like that. So by default, to prove that triangles are similar, you're going to use angles. So if all the corresponding angles in both triangles are equal, they are similar. Okay, AGF and ABC. Let's highlight those triangles. Okay, so that is AGF and ABC that they spoke about here. Okay, AGF and ABC. How can these be similar? Okay, if we can show them that all the corresponding angles in these triangles are equal, then it's indeed similar. So we're going to focus on these angles, so like that angle and that angle and so on. Okay, we already see lots of x's here. For example, in this triangle, we've got an x. Great. In this triangle, we also have an x. Okay, so those two are equal. Okay, what else is equal? If you ever get lost with these parts, grade 12s, what you can do is they really help you a lot with the naming of the triangles. The minute they tell you, prove that this is similar to this, you can already assume, okay, you already know that they have written it in the correct order. So it's similar in this way, meaning the A of that triangle, this triangle, is equal to the A of that triangle, and the G of this triangle is equal to the B of this triangle, and the F of this is equal to the C of this. Okay, so this is really what I mean by that. With these two triangles, with AGF, it means that this A is actually equal to this A. You're just going to have to try to see how that is possible. And then because it says AGF and an ABC, this G is equal to this B. We just have to find out how that is possible. And by already doing that, I can already see what's going on here. You see the butterfly theorem, or angles in the same segment theorem over there. We have two corresponding angles in both triangles equal. That would just make the third angle by default equal. So we have already got it. We've got these two angles being equal and these two angles being equal. Okay, so that makes this by default equal to this. Okay, let's go ahead and start writing. So now we're just going to neatly put that down. Tell them in triangle AGF and triangle ABC. And let's just try to keep it like all the sides in A, or all the angles in AGF, we leave it on this side. So what we first saw in these two triangles in AGF, this angle X is equal to this angle X. So we'll tell them that angle AFG is equal to angle C1. Okay, so that's the first thing. AFG is equal to angle C1. That is not something we have to prove. It's because they were both equal to X. So you can say proven. If you like, you can show them that they were both equal to X. But we already saw that. Okay, and this is a proven angle specifically. The second angle that we saw was equal in both was because of the angles in the same segment theorem. Okay, angle B2 is equal to angle G. Okay, let's tell them that. Angle B2 is equal to angle G, but we'll say angle G here since it belongs to AFG, and then is equal to angle B2. Okay, and the reason is because of angles in the same segment are equal. Okay, and then by default, it makes the last angles in both triangles equal. Okay, because all the angles in the triangles need to add up to 180 degrees. So by default, it's exactly the same since you already have two angles in both triangles being equal. Okay, so we mentioned that one and that one, this one and this one. So the only ones left will be these two angles. So that therefore concludes that A2 is equal to A3. So say A3 equals A2 to put it in the same order. Angle A3 equals angle A2. There's two reasons you can use for this. You can say third angle in a triangle or the sum of interior angles in the triangle. So I'm just going to say third angle in a triangle. And there we go. And now we can conclude. Therefore, this concludes that triangle AGF really is similar to triangle ABC. And done. And the reason is because we have three corresponding angles being equal. Angle, angle, angle. Okay, so that is it for 11.3. And then we move on to the last question, 11.4. Okay, we are finally on the last question 11.4, which says, prove that GF squared is equal to BC times, FCA times AF, and then over AD. So with these, what we can just do is really just find out where these lines are coming from. However, first, I like to actually just go with what it could be, okay, the situation that we probably have here. And it's usually a case where it has something to do with the previous question. So you see the previous answer was this, where we can see that these two are similar. And so we can use the proportions. Okay, so we can actually start with that. Let's actually start with that and see whether that works out, whether we can see any of these there. What I just did now, going for the answer that is more likely to work, is kind of like guessing, which is not a good idea. I just go with it because The route they take is usually something that you guess, okay? But you should never rely on guessing. And this is probably something we need to just keep in mind. Never rely on guessing. Let's actually look at these sides for what they are. Okay, so I'm going to highlight the sides as I see them in the diagram, and then let's actually make sense of it like that. Okay, so BC. Okay, GF first of all. So we've got GF, but it appears twice. So that's GF. And then I'll just use another color to highlight GF again. And then we have BC, right? Times BC. So where's BC? BC is over here. Okay. And then we have FC. FC is over here. Then AF. AF is here all the way down like that. And then we have AD lastly. So AD is over here. Okay. So we have highlighted all the sides that was mentioned here. The 6 sides in general. Okay. Or 5 sides because that's just the same side. And now we're going to look at our diagram and see which triangles or sides or, proportions they are probably using here. Okay, so I would have liked to use the proportionality theorem, but you see that with that triangle, right, that works with the proportionality theorem, with this triangle over here, they are only using AD and AF. That's all they're using. So it's not a good idea to go with that because now you have AC and AG. So you're introducing 2 sides that are not even in this equation. So let's not go there and let's not complicate things. So the only solution now is to use these as triangles. Let's look at all the sides and find out which triangles they belong to. Okay, so we can look at BC. BC, that has to belong to this triangle, ABC. Okay, and to be able to use that triangle ABC, it needs to be similar to another triangle, okay? Because we're going to be using the proportions of these triangles. So we already knew that ABC, right? We already proved that ABC was similar to this triangle AGF. And we can actually just start looking at all these triangles like that. So yeah, we're going to need a lot of colors here. What we're going to look at is ABC, this triangle here, right? And we're going to call it ABC. I'm just going to name all the triangles that are clearly being used here. So ABC, and we're going to put it like this, triangle ABC. So I'm going to try to name everything in this order. Okay, so we have ABC highlighted. Now remember, this is going to be dependent on the sides that we have. We're only taking ABC because we see the side BC. So it belongs to the triangle ABC. Another side that we have is GF. Now, GF appears twice, okay? So GF, but do you see now GF and AF, they both appear in the same triangle, which is the triangle AGF. So AGF is definitely included in the story. But we also know that AGF is similar to triangle ABC. So let's actually write them in that order. So we have ABC and then we have AGF. It's going in the same order, you see, from A to that with a double angle. That's why it's good to always make markings on your diagrams. So A to the double line to the X again, from this angle to the double line to the X. So we're also going to write it in that order, AGF. Okay, so we're going to include that. Let's outline that. Okay, so we're still looking at the sides, right, that are highlighted. Then over here, we see that GF is highlighted again, but we also highlighted this line CF because it's included in the equation, right? CF. So the only triangle that this could belong to is this triangle over here. Okay, so we're going to have to see how does that relate to all these other triangles that we have. When you're looking at this triangle on the bottom, it is similar to this one. Okay, so look at what's going on here. You have an X because these were vertically opposite. You have that double angle because of, well, the double line, that's what I'm talking about there, because of the angles in the same segments were equal. So you got 2 angles being equal, and then by default, the third angle will be equal. So this angle is equal to this angle. So that makes those 2 similar as well. Okay, so we're probably going to have to show them that. Right now, we're just mapping out what we're going to do. Okay, so it's going to be with this, and we have to name it in order as well. So it's this triangle here, clearly, that we're using because it involves 2 sides in that triangle. So since we named this one as ABC, from here to the double line to the angle X, we're also going to have to name this like that. So FGC, that's going to be the name of that. So FGC. It's important to name them correctly so that when you make them similar, you're able to use their proportions correctly as well. So we still have to make those similar. Okay, I'll just put that there so I remember. We still have to show that these two are similar. Okay, but definitely this triangle is involved as well based on the sides that they used. Okay, lastly, we have another, let's just look at the other sides that were involved. So we got all of these, that was involved, the two GFs, right? The FC. But then we also have AF. Okay, AF is fine because it belongs to the bigger triangle, as you can see. But then you have AD. Where did AD come from? Which triangle does it belong to? AD, as you can see, only belongs to this triangle on top. So how does this triangle relate with all the other triangles that we have here? Let's look at that. Okay, you see with this triangle, do you see that we have something that we can actually use here? These lines are parallel, right? So it means that you have corresponding angles here. So this angle is equal to this angle G. We can make that marking, okay? So we're going to have to show them that. We're going to have to show them that that's also equal to angle G. And now because it's equal to angle G, it has angle G, right? It has that X, and then it has this angle over here. So we can clearly see now that it's also similar to this triangle and all the other triangles here as well. Okay, so let's write it in order. It is triangle, and we're going to go from the one that is not marked to the one with two lines to X. Okay, so ACD, ACD. And we still have to show that it's similar as well, and also tell them about that angle, angle C. Okay, so these would be all the triangles that we're going to use. So let's just do the things that we need to do, include the stuff that we need to include, and then let's move on. Okay, yeah, it seems like a lot of work for 6 marks, but I would have to put it out like that to just think it through rather than, just picking certain sides. Okay, I need to see what actually works out and just see them out like that. Okay, so because we can't assume things, let's just show them which things are similar so that we can actually use all these triangles, okay, because they are actually similar to each other. Okay, so the only ones that we know currently or that we've proven are similar are these two, right? Because they already asked us to prove that AGF was similar to ABC. We have those two being similar. But we can also show them that everything else is also similar to ABC, really. Okay, so if everything else is similar to ABC, then they're all similar. Okay, so we can focus on triangle ABC and triangle FGC, okay, because that's the one we don't really have yet. We'll just show them that. So in these two triangles, look at what we have. Okay, that's this triangle and this triangle. Okay, that's what we're focusing on right now. So we can actually erase these markings. It's not really important anymore. So what do we have in these two triangles? You see that those two angles are equal. So we can tell them that angle B2 is equal to angle G. First of all, so we already know that was already proven. So we can tell them proven. It was proven in the previous question. Okay, do you see B2 was already equal to G because of angles in the same segment? So this angle happens to also lie in this triangle and that bigger triangle as well. And then we have two angles being equal to X because they're vertically opposite. So we have that. And we already had that down. It was not here when we were trying to prove those two triangles were, okay, here, there it is. So, okay, it was when we were finding X. So that is already proven. So you can just tell them angle C1 is also equal to angle C4 in these two triangles as well, these two highlighted in red triangles. So that is also proven. We don't have to tell them the reasons, proven. And then by default, their third angle would be equal. Okay, so their third angle being angle A2 and angle F2 would be equal. So angle A2 is equal to angle F2. And so it's because it's a third angle in a triangle. Okay, so that concludes that these two are similar. So we're saying that triangle that is similar to this triangle because, of course, of angle, angle, angle. So that's there. I'm just putting down whatever needs to be put down first before continuing with this because I don't want to assume things. And then we have this situation where, so we're done with these two. We've proven they're similar. We can move on. Now, this one, how does it relate to everything else? So that's this triangle ACD. Okay, so ACD. Okay, so that triangle. And now, how does that relate with the other triangles we have? Okay, do you see that we were able to show that these two are equal because of corresponding angles? We have not shown them that yet. Of course, we haven't written it down, but we saw that now in the diagram. So we can match it like this. This triangle is definitely similar to this triangle. I don't see a reason to prove that. Okay, so we can go ahead and just show them that. So in those two triangles, that is the triangle AGF, this triangle, and in this triangle ACD. Okay, so with this, I'm actually starting to see that this is unnecessary. This is an unnecessary step that we're taking here. We don't have to prove to them that this is similar to that. Okay, by the proof of the proportionality theorem, those two are already similar. So we can just conclude that they are similar. So I'm just going to also tell them that those two are similar. The only thing we can tell them is about those corresponding angles, because the thing is, they already told us that these two lines are parallel. So of course, ACD is similar to AGF. That's how we go about proving the proportionality theorem. Okay, so we can just show them that angle C2 is equal to angle G and then conclude that they are similar. So angle C2 is also equal to angle G. Therefore, this means that these two triangles are similar. So those are triangles ACD and AGF. Okay, so ACD is indeed similar to AGF. Okay, let's just see that it's written in the same order. Yeah, AGF, ACD. Okay, so here's the thing. All of these triangles are similar. Do you see how they all go from one angle to the angle with two lines to X? Same thing here, from one angle, two lines to X. One angle, two lines to X. Okay, so they're all similar. And of course, the little one inside there. Okay, one angle with two lines to X. So all these four triangles are similar. And because of that, we can just conclude that. Let's write that out so we can actually see where these are coming from. Okay, so we start off with triangle ABC is similar to triangle. I'll just go in this order that I wrote them in. AGF. So it's similar to triangle AGF, which is similar to triangle FGC and then ACD. So FGC, which is similar to triangle okay, that was ACD. Okay, ACD. And then just make sure that everything is written the way it should be. Okay, so now that we have said they're all similar, we are going to start getting the proportions. Okay, the reason I do this is so that I can think through the proportions and decide what should stay, what should we not use. It just helps you think this through. Continuing with this, I just want to rewrite this over here so I have something to constantly look back on so I don't lose track of what we're trying to do here. Okay, so we still have exactly what we're trying to prove right here so that we can just compare it. Okay, let's go. When we are working with these proportions, we're just going to write them out. Okay, so these two we can work with together and then we'll just see how they play out and pick specific proportions that will help us to get to this point. Okay, so we have AB over, so first and second with the first and second here. AB over AG should be equal to second and third over second and third. Okay, so BC over GF. Just be careful when working on this section because if you write one letter wrong, then your proportions are not going to work. Okay, so AC is equal to AC over AF. And that's the first pair, okay, of two triangles that are similar. Let's move this down a little. Okay, so we got that pair, great. Now we're going to work with the next pair. So this pair is done. That's this over here. Let's just keep that in mind. Now, the next pair is going to be AGF and FGC. Okay, let's just work with it like that. So these two together. Let's go. So the proportions would be first and second. So that's AG over FG. I should probably stick to one way of naming that. So instead of calling it FG, because I see I just said prove. I didn't say FGF squared. Sorry about that. Okay, so that needs to be there. Okay, so you see that this FG, we can just call it GF so that we are able to keep track of it. So instead of that, we call it GF. Okay, so AG over FG or GF is equal to, now we're going to take the second and third. So that is GF again, as you can see. So GF over, and then over here, it will be GC. Okay, second and third. And then first and last, and first and last. So that is equal to AF over FC. Okay, we are done with this one, that pair, that blue pair. Let's go to the last pair that we have. So that is these two together. Let's mark that in purple. So these two are similar. So their proportions work like this. We can say first and second, so FG, but we're going to call that GF so we can keep track of it, over AC is equal to GC over CD, which is equal to, lastly, FC over AD. Okay, and that's everything that we have. Now, we're going to decide which proportions we are going to use. Okay, so based on what we have here, right, you see, first of all, we have to find a way to form that GF. So that has to be there. GF has to be there. So let's look for places where we see GF. Okay, so GF appears here. It appears here. It appears here. And it appears here. We cannot just go take everything or just take any random one. Now we have to now think about this. Which one specifically can we actually take? So look at whatever other side is with it. In this one, BC is there. So you see how it would be very beneficial to take this, because do you see that BC is included here as well? It's also the position of where it is. GF is on the denominator here, BC is on the numerator. That looks really good, because here, if you had to expand this, what happened is that you had a GF multiplied by a GF, right? Then is equal to BC, and then of course the rest of it, right? So the only way that this could have gotten here, if you had a GF on the denominator, is if you take this GF, because it's multiplying here, and you put it on the denominator. Do you see that that makes perfect sense? That we could have had a situation where we had BC over GF. So I'm going to go ahead and take these two. So I know now that I have BC. That is done. We have the following. We've got one set of GF. We've got BC. Okay. So these other GFs, I will not really, well, I can't say I will not focus on any of them, because this says GF squared. So we still need one more GF. Okay, let's decide which other GF can we take. With this one, it's not too difficult to decide, because the thing is here, you've got GF squared, right? Again, that's GF multiplied by GF. The only way they could have multiplied is if, because you're going to say is equal to something over something. The only way they could have ended up being multiplied is if one of the GFs was on the denominator. Then we cross multiplied, and that's how we got GF squared. Okay. So that would mean, because you see that the GF that we took is on the denominator. So we're going to have to take a GF that is on the numerator. So that already cancels this one out. We're not going to take that. So it's between these two. Let's see which GF would work out here. The GF over GC. Let's check. Do we have GC here? No. Do we have AC? No. Okay. With that one, I'll hold on to that. So we just know it's between those two. Let's just mark them in a different color so they don't confuse us. Okay. Just mark them in red and just hold on to it. We'll decide. Okay. Let's keep moving. So we've got BC. Do we have FC? Let's look around. Do we have FC? Yes, we have FC. I see FC over here. I see FC over here as well. Okay, that's only places that we have it, but we have to choose one. Okay, so FC is here, but rather take a pair, right, that has FC and another letter over here. Yeah, in this case, they both have. Do you see that here we have AF? We also have AF on the numerator, and then we also have AD on the denominator. So let's just think more deeply. Here we've got FC on the numerator, right? In the case that we decide to take this one with AF and FC, could we build that up? Okay, so if you took AF over FC, right, could we actually build this up? In this case, not really. It's not working as well as the way this one would work, because do you see here you already have an FC over AD. That makes that so much easier. So let's not take this FC, let's take this one. Okay, so we'll find something else with AF. So this will take, and so that means we already have AD. Great. Okay, we've got FC and AD, we can tick those off. We've got these two, and then the only thing we must look now for is for AF. Of course, you cannot take this AF because then you'll have an FC, and then that's a bigger problem. You shouldn't have two FCs. You need one because there's only one in this proof, okay, and what they want us to prove. So let's not take that one. Let's look for any other AF that could help us. Okay, I see an AF over here. Great. We've got AF there. And do we have AF anywhere except for this? No. So we could take this one and let's just decide whether it's the only one to take though. It has AC. That's actually good. Here's why it's good that it has AC. Remember that we were still deciding which GF to take. Now we can actually take this one. Here's why. If you take these two together, that AC over AF, it's going to work perfectly with this now because we need one other GF. But now you have an AC that will cancel with that one. Okay. So because it's on the numerator here, but it's on the denominator here. So those can actually multiply. And at the end, we can divide by AC to get rid of it. So now we know which GF we're going to take. That one. Okay, so these are the dimensions we're going to take. A lot of deciding in this one. They don't usually ask questions like this. I have to say this one is new. I've not seen a question like this in a while. Okay, so everything seems fine now. The AF that we have here is on the numerator, but that's fine because we're going to cross multiply since these two are already grouped together. Okay, so let's just take the dimensions that we have. Now remember, guys, you cannot take you can't say BC over FG equals AC over AF and say this can also be equal to GF over AC. That's not possible, okay? These work together. You can equate any of these together, meaning this one can be equated to that, this can be equal to that, and the other way around as well. But they can't go across like that. I would explain that, but that will make this explanation really long. Okay, so we're going to have these together and then these together. So we're going to take GF over AC, and that is equal to FC over AD. Okay, so that's how we're going to use them. We can't make them equal to each other. Okay, they are related to the separate triangles that we are referring to when we say these two triangles are similar. Okay, so let's get multiplying because that's what happens here. And let's see what we get. So when we cross multiply here, we're going to get BC times AF, which is BC times AF. And then let's rather put the GF here because it starts with GF, that proof. So GF times AC is GF times AC is equal to, and then BC times AF. Okay. And then the second equation we will have, because of those dimensions, is going to be, again, I'm going to start with the GF. So GF times AD. GF times AD is equal to AC times FC. Okay, great. We have these. Now, remember, what we need to prove is this. We need to prove to them that GF squared is equal to all of that. Notice GF is squared. The only way that could have happened, and you see none of these are squared, is because you multiplied one equation that had GF with the other equation with GF. So we're going to multiply these two equations together. Okay, so I guess we can just call them equation 1 and equation 2. So that is equation 1 and equation 2. And we're going to multiply equation 1 times equation 2. And this is what we get. So equation 1's left-hand side is going to multiply with the left-hand side. So that is the GF times the GF, which now gives us GF squared. And then AC, so times AC, and then times AD. There we go. We have multiplied the left-hand side. And now the right-hand side. Right-hand side times right-hand side. So it's equal to, so BC times that just stays BC times AC. I mean, we can just try to follow their order. They start with BC and then FC. Yeah. Okay, so we can go BC times FC, because they will just all be here multiplied, times AF times, and then we have AC. Okay, so everything is multiplied here. We've got BC, we've got FC, got AF and AC. Everything is here. Okay, so now how do we get this to look like this? Now, at this point, remember that everything that is here is already here. We only have one thing that is unnecessary here, okay? Which we already caught. It was AC. But we said it's fine. It's going to cancel anyways. We can get rid of it. So it's only the AC that shouldn't be here. But you see that it's on both sides of the equation. So to get rid of it, you can just divide both sides by AC. So there, if we divide both sides by AC, I'll just write another line instead of just concluding on what we should do. At this point, we can just go, okay, this is GF squared. And now those cancel. And you have times AD is equal to BC times FC times AF. And then those cancel. So you see what we have now? What is the only thing we need to do at this point? Do you see that in what we have to prove, the AD is on the denominator? So put it on the denominator. So to put it there, you're going to divide both hand sides by AD, because it's an equation. What you do on the one side, you must do on the other side. So therefore, finally, GF squared is equal to BC multiplied by FC times AF all over AD. And we have proven exactly what they want us to prove. Okay, so that was a very different kind of thing. It wasn't like the obvious option this time. But yeah, so that's how we prove that. There would also be different ways depending on how you structure those triangles, really. Okay, so that is it for this video, grade 12s. All the best for your future tests and exams, and I will see you guys in the future videos.